Welcome back to Analysis from Home. Today we're going to talk about infinite limits. So we've talked already about the convergence of sequences to a limit a. If an is a sequence, we say an converges to a limit a, and we write the limit as n goes to infinity of an is a, if this whole thing is true. This statement says that no matter how close you want an to be to a, that it does get within that distance eventually. That is for all n greater than some threshold value cap n here. Now, we also sometimes would like to say that the limit of a sequence is equal to infinity. So for example, if we take the limit as n goes to infinity of n squared, then we also sometimes would like to say that the limit of a sequence is equal to infinity. We would like to say as n approaches infinity, n squared goes to infinity. The first thing you have to understand is that this does not fit the mold of this definition for lots of reasons. First of all, infinity is simply not a number. This is about what happens in a relationship between a sequence and a number a, and this cap a has to be a number. So the fact that infinity is not a number means that this definition cannot apply to infinity sort of plugged in for a. Also, we can't subtract with infinity primarily because it's not a number, and we can't measure the distance between an and infinity because infinity is not a number. So nothing about this definition informs what we mean when we say this. So what we need is we need a new definition of what it means for a sequence to approach infinity as n goes to infinity. So this will be a new definition. So again, it will apply to a generic sequence. Let an be a sequence. Now, because sequences like this do not actually converge, we're going to say that it diverges, but we're going to say that it diverges to infinity, which is a little bit of a strange language because diverge to seems a little bit of a contradiction. But we're going to, because it approaches infinity but doesn't converge, we're going to say that it diverges to infinity. So we say an diverges to infinity and write the limit of an is equal to infinity if, and now we need a new definition because this one can't apply. So what does it mean to say that it approaches infinity? What it really means is to say that it gets bigger and bigger and bigger. How big does it need to get? As big as you want. So instead of getting as close as you want to the target value a, that proximity measured by epsilon, what we're going to say is we get as big as we want. And that size is going to be measured by some value cap m. So if for every cap m, there exists a cap n, such that for all n in the naturals, if n exceeds cap n, then we're simply going to say that an exceeds cap m. So here, cap m is like a challenge marker. Can the sequence beat this threshold? And we beat that challenge by having the terms of the sequence not only exceed that threshold, but then be forevermore beyond that threshold. This definition is saying wherever you place a threshold along the real line, then the sequence terms might not be greater than that. So let's place a challenge here. The sequence terms might not be greater than that at first, but then eventually they will become greater than m, and they will remain forevermore greater than m. So this might be an here, and then forevermore for any n greater than that, then we would remain beyond cap m. So this is what it means. This is what we will mean when we say that the sequence diverges to infinity. Now, the notation is suggestive, but can cause some confusion. Here we're saying the limit of an as n goes to infinity is infinity, and here we're saying the limit of an as n goes to infinity is cap a. In this case of a divergent sequence, this notation does not mean the same thing as this notation. This says that this thing equals a real number, and this is kind of nuanced. This doesn't really mean that this thing is a defined real number. What it really means is this statement. So let's see if we can do an example. So let's take this example, because I think we will agree that the limit of n squared as n goes to infinity is infinity. And let's see if we can prove on the basis of this definition that n squared approaches infinity. So we've done a lot of proofs of sequence convergence using this definition of the limit. And from all of those proofs, we've developed a strategy for proving them. And I've tried to make the point that although the strategy gives us a boilerplate for how that works, we don't really need to memorize that because the structure of the statement teaches you how you have to prove the statement. And the same is true here. This is our very first example of a proof that a sequence diverges to infinity. But even so, you should know how to begin because the logical form of the statement here is for every m, etc. Then in order to prove this, then we should begin with let m be something. So let's start with a claim. Our claim will be that the limit of n squared as n approaches infinity is infinite. And then we'll prove this. And hopefully I have enough room here. So the proof of this claim is the proof of this, which naturally begins with let m be arbitrary. So let m be an arbitrary real number. Now the proof must continue with a choice of cap n, and as usual, we won't know how to choose cap n until we've done some future work. So we're going to do what we always do. We're going to leave a little bit of blank space in case there's some cleverness required, and we're going to say let cap n equals blank, and I'm going to fill in that blank later, right? Then this statement continues for every n. So let's continue. Let little n be a natural number. The statement continues if little n exceeds cap n. So we should continue assume little n exceeds cap n. And now here's where the work happens. But what we'll find here is it's actually easier than this case where the limit is an actual real number of a convergence sequence. The primary reason this is going to be easier is because there are no absolute values here. The combination of absolute values and inequalities can cause some trouble here. But this statement doesn't have any absolute values, so that's the good news. What we need to show is that an is greater than m. So this is exactly analogous to the point where we get here and we have to write down this thing is less than epsilon. And when I do that, I tend to write down this thing and then compute for a while and then eventually attempt to show that it's less than epsilon. Here, what we're going to do is we're going to write down this thing and then we're going to compute for a while. And instead of putting a less than epsilon here, as I would if I were doing this thing, I'm going to put is greater than m here. So I'm going to put an, I'm attempting to show that an is greater than m. Notice that I'm not doing an minus a, and I don't have absolute value signs because they don't appear in the definition. They appear in this definition, but they don't have an analog in this definition. Notice furthermore that the inequality that we go for when we're showing that a sequence converges to A is a less than epsilon. But this inequality is a greater than m because we're trying to show that the limit, that the sequence terms eventually exceed any given value. And so that means that if we're shooting for a greater than, then as we compute here, we can have equals, equals, equals. Any equals appearing in this computation is fine. Any greater than or equal appearing in this computation is fine because it will assist us in eventually proving greater than. Any greater than is fine, but what we mustn't have is a less than or a less than or equal to. And I want to call your attention to that because it's the opposite of the situation here. That means that as these terms go and as we recompute and change these things, we are entitled to make them smaller if we desire. We can make this, n squared, we can make it something less than n squared and insert a greater than or equal to as we go along. This is the opposite of what we're entitled to do here because we're shooting for a less than sign. We're here, in this case, we're entitled to allow the terms to grow slightly. Here, we're entitled to let them shrink slightly. So now here, there really isn't very much algebra to do. We just need to say that n squared is greater than m. And then we need to say provided. Now, when will n squared be greater than m? N squared will be greater than m provided that n is greater than the square root of m. Now, so almost, we'll get to a little sticky point in a moment. So if n is greater than the square root of m, then indeed n squared will be greater than m. And that's all that we really need. Now, there is one small possible error with this proof. And the possible error here is what if m is negative? If m is negative, then when I say the square root of m, then that doesn't really mean anything. But if m is negative, then n is automatically n squared is automatically going to be greater than m, because remember, n itself is a natural number and is therefore positive. So provided that n is a natural number, this equation will be true either because n is greater than the square root of m, or because m is negative and n is positive. So we don't need to worry about the case when m is a negative number here. So provided that n is greater than the square root of m, we will have this thing true. However, we do need to maybe be a little bit careful, because as long as we're saying the square root of m, we need to be reassured that the square root of m exists. And so we should have a sort of a bailout condition. So, or n is greater than 0 if m is negative. So here, I don't want to say square root of m at all if m is negative. So this is kind of my way around that. Now, this tells me that so long as n exceeds this value, then n squared exceeds m, which is what I'm trying to show. And that tells me how to choose cap n. I'm going to choose cap n to be the square root of m if m is positive, and I'm going to choose it to be 0 if cap m is less than or equal to 0. So if cap m were to be negative, then I couldn't choose it to be square root of m, but I can choose it to be 0 in that case, and everything will work. So long as n is greater than that value, whatever it should be, then n squared will exceed cap m, and that proves that this sequence diverges to infinity. Let's do one more example, a slightly more complicated example in which we might have to manipulate some algebra. I just want to show how some of the algebra can work here. So let's let an be n squared plus 1 divided by the square root of n. And we'll claim that the limit of an is equal to infinity. In other words, this sequence diverges to infinity. So we'll start in the usual way. So let's let m be a real number, and we're going to choose n, and I don't know yet how to choose n. We're going to let n be a natural number, and we're going to assume that n exceeds cap n. And then we're going to compute an, and we're going to hope to show that it exceeds cap m. So we're going to compute an, and we will compute it, of course, it will be n squared plus 1 over the square root of n. Now, of course, we don't have any absolute values this time, but we do have a complicated mess to figure out, and we want to show that this is greater than m. Now, I can do equals, equals, equals. There's no obvious algebraic simplification that can be applied here, and so I might want to use some less than or equal to's, or rather some greater than or equal to, some inequalities, so that I can get this thing simplified a little bit. Now, the inequalities that I'm entitled to are inequalities of this form, greater than or equal to, opposite of what we're used to, because we're trying to show eventually that it's greater than m. And that means that, so the way I think about it, we commit to the inequality first, right? We don't think about what changes we want to make first. We think about what inequality we're allowed to write first, and then we let that guide the changes that we are allowed to make here. This is entitled to be a greater than or equal to, because that's what we're proving. That means that this thing is entitled to shrink a little bit. Now, we don't want to just shrink it down to 1 and be done with it, because then it won't go bigger than m. But we want to shrink it a little bit, to simplify it a little bit, and make it more manageable. That means that anything we can do to keep the fact that it basically diverges to infinity, but make it slightly simpler and smaller, is going to be productive here. So what can we do to make this simpler and smaller? Well, we can just drop this 1, right? That 1 in the numerator is clearly not going to have much of an effect on the long-term behavior of the sequence, but it's increasing the numerator. And if we drop it, the numerator will go down and the whole fraction will go down. And so if we drop this 1, then we will make it smaller, but it's also much simpler to manage. Now, this is equal to n squared over n to the 1/2 power. And so we can use our rules of exponents on that. That's n to the 3/2 power. Now, here there are two different ways to go here. One way to go is we can say, okay, n to the 3/2 is greater than m precisely when n is greater than m to the 2/3 power by raising both sides to the 2/3 power. That's one way to go. That works just fine. Another way to go is simply to say that n to the 3/2 is n times the square root of n, right? That's n to the 1 and n to the 1/2, which is n to the 3/2. And the square root of n is at least 1. So this thing is greater than or equal to n itself. So here what I'm doing is I'm aggressively using more inequalities to simplify this down to an even simpler thing. And then the comparison between n itself and m is going to be very obvious. The n will be greater than m precisely when n is greater than m, right? There's nothing else to say. So this is going to be greater than m, and then that's provided, of course, and this sounds a little silly to say, but it's provided n is greater than m, right? So this is always true for n natural, always true, always true, always true, always true for n natural, and then this is true only when n is greater than m. And that gives us the threshold that we need for cap n. It's m itself. This was not the only way to do it. We could have stopped here, raised both sides to the 2/3 power, and then our cap n would have been m to the 2/3 power. But it doesn't really matter how you do it, so long as you get a proof that's functional here. So this demonstrates that the sequence an diverges to infinity, which essentially means no matter how big you want these terms to be, you can get them to exceed and forevermore exceed any given value cap m. Now, the moment we start writing limits and writing infinity on the right-hand side of these limits, then we have a problem with previous work. So I want to recall to you some of the previous stuff that we've done. I'm going to point out to you how this new stuff syncs or doesn't sync with that previous work. In particular, what I'm talking about is the limit laws that we've discussed, and there have been so many of them. So here are the limit laws for limits of sequences. If we have a sequence an which converges to a and a sequence bn which converges to b, then we add the sequence terms and we get a new sequence an plus bn, and it converges to a plus b. We subtract the sequence terms and get a new sequence an minus bn, and it converges to a minus b. We multiply the terms or divide the terms, and we get sequences that converge to a times b or a divided by b. This, of course, is only if b is non-zero. So if b equals 0, that doesn't work. So here are the limit laws, and we've proved these. Now, how does this relate to the new material limits when limits are allowed to equal infinity? Well, the key for you to understand is it really just doesn't. These limit laws presume that the sequence an and the sequence bn converge. So in other words, they presume that they get closer and closer to a specific real number a and b in these limit laws have to be real numbers. They cannot be the artificial symbol sideways 8 infinity, right? They do not apply in the case of divergence to infinity. And this makes a big difference because that means that, for example, if we have a sequence an that diverges to infinity and a sequence bn that diverges to infinity, you might presume that the sum of those sequences an plus bn diverges to infinity too, and you might say it's infinity plus infinity, but it would be wrong to infer that from the limit laws. If you go back and look at the proofs of the limit laws, they begin by presuming that an converges to a, and we have the usual traditional definition of convergence, right? For every epsilon greater than 0, and it ends with an minus a absolute value less than epsilon. So these are completely about convergent sequences. These are not about divergent sequences. And if you apply the limit laws to something that ends up showing you an infinite limit, then you have applied them incorrectly. They only apply in cases when these things actually converge. So the key to understand here is that the limit laws, as discussed already, do not apply to any sequences in which the limit is infinity because they are only about convergent sequences. On the other hand, we do expect some truths about limits of infinite sequences too. And so there are actually a few limit laws that apply to infinite limits as well. So what we have to do is we have to state those separately. So there are three important limit laws that I'd like to discuss for infinite sequences. So for infinite limits. The first is a sum law. So I'm going to say let an and bn be sequences with the limit of an is equal to infinity and the limit of bn is equal to infinity. So these are both divergent sequences, which is in contrast to the traditional limit laws setup. Then we do have a bit of a sum law. The limit of an plus bn is then equal to infinity. What else would it be? If an is getting larger and larger and larger, if bn is also getting larger and larger and larger, then the sum of them, an plus bn, is getting larger and larger and larger, and so we would expect that it diverges to infinity. So that's the first statement here. The next statement that will be some reassurance is that the product of those two sequences is equal to infinity. So let's just stop with these two, and we're going to pause to prove these, and then we're going to prove a comparison test for infinite limits. So how do we prove the sum law? Well, the proof of the sum law for convergent sequences was actually kind of hard. And part of the reason that it was hard was that it involved absolute values and the triangle inequality. The proof of the sum law and product laws for divergent sequences are actually quite easy. And the reason is fundamentally because they only involve one inequality, an is greater than m, and also because they don't involve any absolute value signs. So I'm going to play a little trick here. I'm going to prove them both at the same time. So I'm going to show you the proof of the sum law, and then I'm going to change it up at the last minute, and it will accidentally be converted into a proof of the product law. So let's go ahead and do this. So we're going to assume, what are we assuming? So we're assuming that the limit of an is equal to infinity, and we're assuming that the limit of bn is equal to infinity. Now, I want to remind you, because it bears repeating, that this does not assert that infinity is a number. I'm not saying that infinity is a real number. You cannot add these or manipulate them algebraically at all. This is just a notation that means that effectively that this thing gets larger and larger and larger. It's a notation, to be more specific, to be more direct, it's a notation that means this. It means for all m, there exists a cap n, such that for every n in the naturals, if n is greater than cap n, then an is greater than m. If you're worried about what this means, if it's blowing your mind to think about the infinite, it means this. It abbreviates this, okay? And there is no infinity symbol in this, of course, right? There is a cap m, and you can exceed cap m and stay forevermore greater than cap m. So you don't need to worry about the spooky, I don't know, difficulty, the metaphysical complexities of the infinite here. You just have to think that this is an abbreviation for this. And then this line here is an abbreviation for the exact same line, but with a bn in place of an an. So we get this thing. So bn exceeds m. These are the assumptions here that we've got, and we're trying to show this where we're trying to prove the same thing with an an plus bn in place here. So the goal is to prove that for every m, there exists a cap n such that for every natural n, if n exceeds cap n, then an plus bn exceeds m. Now, all right, let's get started. So that's what we're going to show. This is what we've assumed. And so how do we show that? Well, there's only one natural way to begin, and that is to let m be arbitrary. So let m be a real number. And then, of course, there has to be some cleverness. And after the cleverness, then I have to choose some value of cap n, and I'll have to proceed with the proof before I am clever enough to appropriately choose the value of cap n. But something will happen down here that will guide my choice up here. But then after choosing cap n, then it's clear what I have to do. I have to let little n be a natural number. I have to assume that little n exceeds cap n. And then I have to compute something about an plus bn. So I'm trying to show that an plus bn exceeds cap m. Now, I have the power to make an bigger than cap m all by itself. So let's actually use it here. Let's make an bigger than cap m and not worry about bn. Can we do that? Well, not exactly, because bn could be negative. So even if we make an itself bigger than cap m, we still have to get some control over bn. We need it to at least be positive, so that when we add bn to this, can we make bn positive? Sure, because this is true when m equals 0, just as much as it's true for any cap m. So the plan here is I'm going to control an so that an is greater than cap m all by itself. I'm going to control bn so that bn is greater than 0, which I can do because this is for all m. So I can certainly make it greater than 0. That's sort of the easy thing to do. And then I'm going to add them up, and I'm going to get them greater than m. Now, I'm actually going to go a little bit over the top here. Instead of controlling bn to be greater than 0, I'm going to control bn to be greater than 1. And you'll see why shortly. So how do we get that level of control? We have to invoke these definitions here. And these invocations should appear here. So we're going to choose an n1 for cap m. Notice cap m is already decided in this proof at this point, so we can do this. So we're going to choose that in the definition of the limit of an is infinity. And we're going to choose some n2 for m equals 1 in the definition of the limit of bn is equal to infinity. So basically, I'm choosing a cap n2 beyond which the terms bn are greater than 1. Now, I said I needed them greater than 0, but I'm actually forcing them greater than 1, and that might cause you some confusion, but hold on, we'll get to that. So with those things being chosen, then I'm going to choose n, of course, to be the max of n1 and n2. So I've got two different independent levels of control here. The n1 gives me control over an, the n2 gives me control over bn, and then so long as n is greater than cap n, which is equal to the max of those, then n will be greater than each of them, and then all of this stuff will be true. So in other words, so long as n is greater than cap n, an will indeed be greater than m, and bn will indeed be greater than 1. So then this thing is going to be greater than m plus 1, which is greater than m, and that is as desired. So that completes the proof of the sum law and shows how we make these choices for n1 and n2, and then we can get this thing to be greater than m. And that's all we need to do for the sum law. Now, I did choose cap m to be 1 there for b, and it still may seem a little bit mysterious. I could equally have said this is greater than m plus 0, which is equal to m, and that would have worked too. The reason I did that is because I want this whole thing to also function as a proof of the product rule. So this is like two overlapping proofs here. I just didn't want to write it again. So here, what we could do is we could say, or an times bn is greater than m times 1, which is equal to m. And that would be as desired for the product law. So in blue here, what I'm doing is I'm just sort of showing how you would change this proof if instead of the sum law, you wanted the product law. So that gives us the proof of the sum law in black. And if this last black line is replaced with this last blue line, then that gives us the proof of the product law. And that's the entire reason for choosing the 1 here. If I were only interested in the sum law, then I would have chosen 0 here. But if I'm interested in sort of making the same proof work double duty, then it's useful to have a 1 there. Because for the product law, I wouldn't want this to work out to be 0. Okay, so that's a couple new laws for the for infinite limits. And now I want to do one more law, which is the comparison law. And then after that, a rule about what happens when you diverge to infinity, take the reciprocal of that, then we would expect that to go to 0. And that's exactly what's going to happen. We'll do those things in the next video.